Okay, so this video is a remake of a video that I did last week to cover Lab 9 Feather Week 1 warm-up, which is the pre-lab to the formal Lab 9 that you guys do to turn in for the end of the week. So whichever lab week that is. So the previous version of this video was a one camera version that I shot on my cell phone where I panned back and forth between the screen and the kit. However, I got a license for a video screen recorder program to run on Windows. So now I can do a two camera version. This one is essentially the virtual camera that is the screen on my laptop, and the other one is my cell phone that's focused right now on the kits here that are in front of me. So the intent is that you can run these videos side by side and see what's going on both on the screen and with the kit at the same time where that's appropriate. So this video is a companion to the lab, the written pre-lab, the warm-up lab. So it's not strictly necessary. However, the two times we did this lab live over Zoom, there was enough confusion. I don't know if it was just time pressure or what, but there was enough confusion and enough questions, not too many, but that I decided that given that I have the ability to do a two-camera version, that I would go ahead and I would replace the old version. So it's also kind of a mop-up for students that had the Monday lab when I hadn't completed the lab in time for you guys to start it. I think I posted about 30 or 45 minutes into the lab. And so you guys actually started to do the lab that was from last semester, which although 85 or 90% similar to this semester's lab is different enough that I can understand why there'd be some confusion. So I apologize for not getting that lab done in time for the Monday session. So I'm hoping this new version of the video will be especially useful for those students. And I apologize again for them. So I'm going to basically walk through the warm-up lab, as you can see on my computer screen. You may notice that this lab is dated 25th of March. The last one you saw was probably 23rd of March. In the two sessions we did live on Zoom, we uncovered a couple of small problems, which I actually fixed in this version of the lab. If I can remember what those differences were, I will call them out. There may be a day or two delay in getting a PDF made of the Jupyter Notebook version, which is actually how I authored these labs. Dr. Asan makes PDFs from them and posts them. So if only the 23rd March version is available, it is 97, 98% complete. It did answer a couple of questions that came up in the lab, but they aren't fatal. So if you don't see the 25th version up there, don't sweat it too much, and it should be coming up shortly. So let's start in on the lab, on the warm-up lab. So the first part of the lab that I'm going to go through is this kit smoke test. For those of you who don't know what a smoke test is, smoke test is the test you do when you come up with a new piece of hardware. It could be mechanical, could be electrical, where you basically plug it in for the first time, and if it smokes, you know you didn't do it right. And if it doesn't smoke, then okay, well, it's time to actually start testing whatever it was that you worked on. So this is the test to make sure your kit doesn't smoke when you plug it into your laptop. So let us look over here in File Manager. I'm going to show you my left pane here. It's very similar for Mac OS, but I have basically kind of two hard volumes. I've got my local disk, and I happen to have a SD card plugged in. So before you plug in the kit, this is typically something like you'll see on both Mac OS and Windows. I'm going to go ahead and I'm going to plug in the kit, and I'm going to use the order that I advertised in the safe handling document that you guys should have already read. I typically plug my kit end in first, and then I plug the other end into my laptop. So watch the left pane in the File Manager when I plug this in. And you will see that on Windows, it pops up this annoying will never go away dialog box every time you plug it in. And over here showed up a new volume called CircuitPy. So the way the kit works, and this is really cool, is that when you plug the kit into USB, it represents itself to the laptop as a flash stick, which is super cool because updating software on your flash stick is just as easy. On your Feather kit is just as easy as copying software over onto a flash stick. You can delete files, you can copy files over, you can even edit files in place. And we'll be doing that later on in the demo. However, I do warn you that in the text document of the lab, that the files that I put on here for your kits when I delivered them to you are actually already out of date. So the first thing the lab instructs you to do is to basically just go ahead and nuke them. So we're going to update your files. So you just take them, select them all, hit delete. I use the delete key. I said I use the delete key. Okay, I guess I'm going to use right click. And delete them all. Now we need adequate replacements. Go to the Files section of the course website, and down in the Spring 20 Labs ME30 Lab 9 Feather Lab directory is the original version of the demo program and a updated one. So go ahead and grab the updated one. By the time you see this video, I may have deleted this file, so don't expect to see it. All you need to do is click on it, click the download link, and it's extremely small, so it'll download very quickly. I think I pressed save download twice, so yep, there it is. Okay, close that, go back out to File Manager, go into my Downloads directory, and there's the zip file. So hopefully most, if not all of you know what a zip file is. However, I already did run into one student who didn't know what it is. So a zip file is basically just a collection of files that I'd like to pass from one person to another, and a utility called zip smashes them all together into one file, which is called a zip file, which you can see from the extension here. Now on Windows, all you need to do is double click on this, and File Manager makes it look like it was a directory, and it just shows you what the contents of that zip file was. So these are all the files that went into that zip file. So if we go back and look at the CircuitPy volume, you'll see it's empty because we deleted everything that was in there. If we go back to my downloads directory, okay, so I'm looking into the zip file now. So I'm going to just take the files that are in the zip file, and I'm going to drag and drop them over onto my CircuitPy volume. Easy peasy. Now I'm going to focus on my CircuitPy volume, and there are all the files. So one thing that some students do is they put the zip file over here. That's not what you want. Sometimes if you're using a zip utility and you extract the files from the zip file into your CircuitPy volume as its destination folder, it will put all the files in the zip file under another directory. So instead of seeing the files that you see here, you'll see a single directory. And if you were to go down into that directory, you'd then see these files. The problem is that that's not what we want. We need to have all these files that are listed here in the CircuitPy root volume, in the root directory of the CircuitPy volume. So if there were a directory between here and these files, it is not going to work. So if that happens, take all these files, move them up into the CircuitPy volume, and then go back up into the CircuitPy volume, and you should see everything just like we're looking at here. So you've updated all the software that's on your Featherboard. Well, not all of it, but all the code we'll be writing is on the Featherboard now. So let us go back to the lab and see what the next step is. Updating the files, we have done that. Skip over that. Okay, so I happen to know that the first thing that the program does is it starts flashing LEDs. Now, the last time I used this kit, I had this jumper in the RGB red, green, blue position. To see the flashing LEDs, as you should, you need to put the jumper over the top 2 pins, top meaning oriented like this, the top 2 pins, which is the red position, and you'll see the 2 red LEDs flashing. To me, that's an indicator that the Python program that is installed in your Featherboard is already running. So let's talk about that. When a board is plugged in, when it's powered up, whether it's in this kit or whether it's in a breadboard or whether it's not connected to anything else, the Featherboard runs the Python code that's in code.py. All these other files that are in the Feather volume are helper files that code.py uses. So code.py is the name of the code that gets run by the board. So whenever this file changes, whether it was edited in place, whether it was deleted and a new one drag and dropped over, or if it was, how else can it get there? Extracted from a zip file, doesn't matter how it gets there. As soon as code.py gets plopped onto the board, or actually any other files on the Featherboard get updated, the board resets itself and it starts running code.py from the top again. So I happen to know, because I wrote code.py, that the first thing that it does is basically to flash these 2 LEDs. So at this point, we actually know that the Featherboard works, it's plugged in, we have copied files over to it. So we also know that the USB cable has data wires in it and is not just a charge-only cable. If you got your cable from me, I guarantee you it's a data cable. Data cables are also known as sync cables. So you can be guaranteed that the cable is suitable for copying files over from your PC to the kit. And if you don't see either the CircuitPy volume come up or the program running like this, so you would actually see the program running like this if you had a charge-only cable. Your laptop would be providing power to the kit, and it would have been running the old version of the program, which coincidentally does not start off with these lights flashing. So you wouldn't in fact see this if you had a charge-only cable. You would just see both LEDs being off. So you can actually start pressing the buttons and have them come on, but the current version of the program flashes the LEDs is one of the first things that it does. So all that being said, let's go back to the lab and make sure we're not skipping over anything important. Okay, no, this is about where we are now. So the next thing we're going to do is we're going to install and start to use an editor that is kind of purpose designed to run Python on boards like this. And we'll see why Moo is particularly good at this, rather than using another text editor like either another program editor or something like Notepad or Word, or let's see, on the Mac, that would be TextEdit. I think it's called TextEdit on the Mac. So we're going to go to code.moo or codewith.moo, and there's a download page. I believe the home page looks like this. You click on download to get the download. So it's not intuitively obvious, or I should say it's not blatantly obvious, but there's actually 2 versions of Moo for download on this page. The top introductory paragraph talks about the next alpha version. Alpha is pre-release of Moo, and this version is 1.1. something. And down here where these icons is the previous stable 1.0 release. For the purposes of ME30 and ME106, both of these work just fine. I've used both. I've not run into any problems with the new test version. So I actually kind of encourage you to go ahead and run the new version. Obviously, if you're on Mac OS, this is the guy you want to click on. Pretty much everybody's laptops at this point in time are going to be 64-bit. On 64-bit machines, I tend to encourage people to go ahead and run the 64-bit version of the program. So when you click on this, it's going to go ahead and download it. So it's a decent sized file. Rather than go ahead and download it, I happen to already, through the magic of video, I happen to already have copies of each, the 1.0 and the 1.1 version, already on my laptop. Here we go. So These are the two versions of Moo. I prefer the new test version, so we're going to go ahead and double click on that. And it's going to go ahead and start to install it. And just like in the text version of the documentation, it guides you through the instructions here on how to install it. So for the most part, you're just clicking through like everything, you're accepting the defaults. I prefer to do install just for me. I don't change the directory for the installation, and it takes a minute or so to suck all the files out of the installer and plop them on your disk. I'm gonna have a little drink here. While it's doing that, I will warn you, so this is actually one of the differences between the March 23rd and the March 25th version of the lab. We did have one student in the Wednesday lab running on Mac OS that when she tried to either install Moo or to run it for the first time, she got a big nasty dialog box from Mac OS saying, hey, this is an untrusted app and I don't trust you to run this because I'm Steve Jobs and I know more than you do and you will do what I tell you. Okay, well, he's dead. He actually can't say that. But so the problem is that for some configurations of Mac OS, and I don't know how new this is, but it also varies from machine to machine. There's an option to have it refuse to run untrusted apps. That is, apps that did not come from the Apple App Store. And it basically does that to prevent you from intentionally or unintentionally downloading something that shouldn't be run on the machine, and it's doing the old, are you sure you want to run this program dialog box. So I trust Moo, you should trust Moo, at least this version of Moo is perfectly trustable. You do want to run it. However, I believe that if you get this dialog box on Catalina, I guess, there's no option to just click through that thing. However, I did find on Google that there is a Mac-ish way of getting around that. Ultimately, there is a system setting you can change, and I believe it's documented in the URL that I point out in the lab. But Appendix B was added to the 23rd version lab to the March 25th version. And so for anybody who runs into this issue on Mac OS, look at Appendix B, and there's a URL that tells you how to run Moo and override that dialog box. And I believe the article also specifies how you can change the system settings so that it never pops up that untrusted dialog box again. So Moo is done installing on my slow Windows machine here. So the lab is going to have you, I believe, just go ahead and run it at this point. Yeah, go ahead and install the program, it says. At this point, also confirm that Circuit volume is showing up in File Manager. It is. Then it says, go ahead and launch Moo. So we're going to do that. We're going to go ahead and we're going to launch us some Moo. Okay, so Moo is already showing how fancy it is. So in the previous version, I think of this video, I may have installed the 1.0 version. Before I uninstalled it to make this video, I was running the 1.0 version and there were a few fewer choices in this dialog box. So it may not look exactly like this if you choose to run the 1.0 version. So the cool thing about Moo is not only is it kind of purpose-built to run on hardware, and it shows you a bunch of different hardware that it runs on, the BBC microbit, CircuitPython, which is what we're using. There's an ESP MicroPython. There's some other things here. Moo is smart enough to ask you, especially if you've got a kit plugged in, whether you want to use the kit right away or if you want to program in regular old Python 3. Well, we want to use our kits because that's why we're here. So select where it says CircuitPython. I think the 1.0 version says Adafruit CircuitPython. So select this and hit OK. And I believe in the future, the Moo will just notice that the kit's plugged in, and it'll tell you, hey, do you want me to go right into CircuitPython mode? And if you click yes, it makes CircuitPython mode be the default. So this isn't what you're going to see when you run it. It jumped into code.py because I'm a previous Moo user, but you'll see Moo come up and basically look something like this. Actually, it gives you a code window with one commented line of code. So the first thing we're going to do is we're going to load a file into Moo. This is basically what Open does in any Windows app. So if you notice up here, it says CircuitPy. So I'm looking into my CircuitPy volume and I want to suck in the code.py file contents into my editor window, and I'm going to start editing it, or I could start editing it. So this is code.py. This is the demo program. It's fairly long. It is 312 lines long. Maybe for your final project, you'll have a 300-line program, but maybe not until 106. Are you going to be writing code that's this involved? So that's using Moo to look at the code in the CircuitPy volume on your Featherboard. So next thing it wants to do. Yep, already talked about that. Okay, so let me point out what I'm pointing out in the lab. So down here in the bottom right-hand corner is a status string that tells you what mode you're in. So if for some reason this said Python or Python 3, you would know you're in the wrong mode. You can actually switch modes back and forth between CircuitPython using the board and running and writing regular old Python 3 for the PC just by selecting mode, and it pops you back to this dialog box that you already saw. But when you're in Python 3 mode, it changes the mode down here to Python. We don't want to be there right now, so we're going to go back to Adafruit CircuitPython mode. So there we are, back to where we started. So next part of the lab is the running the kit demo program portion. Okay, so one of the things I talk about here is, so the demo program is here for you to use as long and as many times as you want. As beginning Python programmers and beginning kit users, you're going to be writing fairly simple programs, and some of those programs, even you, are going to be so simple you swear that there couldn't possibly be a bug in the program. And I believe those lights, those LEDs on the board should be blinking, and they're not. So it must be a hardware problem, and I'm going to send Eric an email and tell him my kit's broken. Well, 99.9% of the time, it's a bug in your code. It's not just because it's you or it's ME30, it's not your kid. I do it all the time. I can write 5-line programs that don't work also. So you're going to do this dozens of times between now and when you are a much better Python programmer. You're going to write programs that you swear should work, and it's pretty much never the hardware. So you are always welcome to go back and run the kit demo program, which you'll see in the next 15 or 20 minutes, exercises everything on the board. So if you believe one part of your kit doesn't work, feel free to go back and run the demo program, and it'll almost certainly prove to you that, hey, all that stuff on your kit does in fact work and the bug was really in your program. So I still do this, except I don't bother running the demo program anymore. I know it's me. So I just skip over questioning whether it's the hardware, and I assume it's my bug. And 99.9% of the time, it really is my bug. So got the kids here to go back and do a sanity check if that's what makes you feel good. So all you need to do is download the zip file. I would just recommend keeping that zip file around in wherever you keep your ME30 files. You can always go back to them. So not only can you go back and run it, but you're welcome, obviously, to go and look through the code for ideas of how I do certain things. If you see something that you like how it works and you want to use it for your final project, then feel free to go ahead and scrape code out of that. So what else is in the kit demo program section here? Okay, so one problem that we have almost every lab session is that these files, once again, need to be in the top level directory. So one student actually didn't have them. They had them down in a folder, and they were not seeing these LEDs flashing, which is the first indication that code.py is actually running. So because code.py was in some subordinate directory, he or she wasn't seeing these LED flashing. So we did a screen share, and I was able to look at her circuit high volume, and sure enough, there was a directory there. So you should be seeing this at this point with the jumper in the red position and code.py running, these LEDs should be flashing. If you are seeing nothing, okay, so let's go through some of the things you might see. What you might occasionally see, and one of my boards has this issue, sometimes when I plug it in, I only get this yellow LED next to the USB connector. I'm going to try this a couple times, see if I can reproduce it. Show you what no, it's not going to do it. So trust me, sometimes you'll either only see this LED be flashing or solid, and you won't see this big LED on the blackboard lit. That is definitely an indication that your USB connector isn't seated into the USB connector properly. So if you just unplug it and plug it back in again, you should see the big LED come on. It's usually either solid green or green flashing. And if you're running the demo program as your code.py, of course, you'll see the two LEDs flash. So at this point in the lab, one of the differences between the 1.0 version of the kit and the 1.1 version of the kit make themselves apparent. And the first detour we're going to do is a little bit of a software one. So for 1.0 kit owners, what you need to do is, you can do this in Moo. You'll notice that there's a series of imports. All of them happen to show up on the first screen. There's 3 imports that are commented out, and they have v1.0. These are the 1.0 versions of the files that need to be imported for the 1.0 kit. This is a 1.1 kit, and the majority of the kits are 1.1 kits this semester. So when I created the code.py file originally, I had the 1.1 commented in, and the 1.0 ones commented out. So if you're a 1.0 kit owner, the first thing you have to do is you have to uncomment out your copies of the import files, and you need to comment in the 1.1 version. And you can go ahead and do a save at this point. And now you're basically running a 1.0 adapted version of the demo program. So that's all it takes from a software standpoint to accommodate a 1.0 kit. So I hope you 1.0 folks weren't panicking that you weren't seeing your LEDs flash like that initially. I probably should move that section up earlier in the lab so you guys don't panic. Okay, so because I am running a 1.1 kit, I need to comment out the 1.0 and put back in the 1.1 versions and go ahead and do another save. Okay, so that was that 1.0 kit detour. There's one more, I believe, towards the end of the lab about how the 1.0 and the 1.1 kits work. Now let's actually run the demo program, and that's the section we're in, the now let's actually run the demo program section. So I believe I already explained that when you plug in your board, it immediately starts to run code.py. And it does 2 things, actually. Not only does it flash those LEDs, but it also prints out some messages. So you may be thinking to yourself, so if I'm a hardware kit like this and I do print in my Python program, where does the print output go? There's clearly no display on my kit. Well, one of the features in Moo is it provides a window into which print messages go, and also that any input that you ask for, where it can be typed in. So the way to get that other window, it's called the serial window. It's for serial communications, serial data communications back and forth between the laptop and the board. So if you just press the serial icon, it opens up this second window. Now, I told you that not only does it flash the LEDs, but it prints out some messages. The problem is we miss those messages because the program started, it printed out those messages, and those messages are gone. We don't see them in this window because the window was opened after those messages were printed. So if you remember, I told you it was easy to restart the program just by changing code.py. So if you click back in the code window and you hit save, the board recognizes, and if you could have seen that LED flash. Whenever this LED flashes from like green to red and back and forth a couple times, that's actually it acknowledging that the contents of the file system on your Featherboard has changed. And it's resetting itself and it's restarting and running code.py again. And as you can see, there's now text showing up in this serial window. And these are the messages. Well, the top messages are actually the system part of the board. I'm printing out some stuff. But then it says code.py output. And these two lines are actually generated from print statements in code.py. So they were statements that I wrote. And the text is collected from your print statements. And it is shoehorned into this window. So we're actually going to go ahead and run the program. The program's going to tell us a bunch of things to do, and we're going to dutifully follow along and do what it says. So it tells you to switch the LEDs jumper. If you look on the board right near the jumper that we were already talking about, that jumper is called LEDs. It has two positions, RGB and red. And this is confirming to you that you should have the switch in the jumper in the red position. The difference between the two will become obvious here in about 60 seconds. So the statement is telling you to press each button in any order to light its respective LED, then press SW0 again to continue. So let's go ahead and press each button. I'm going to happen to press this one first, and then this one. So this part of the demo proves to you that both your buttons work and both your LEDs work. So if you were writing a piece of code and you swore that one or the other of those guys didn't work, you could come back and run the demo program, and in the first 5 seconds, you could prove to yourself that both your buttons and your LEDs work. It's always nice. It's always reassuring. So what you may not understand is this message is talking about SW0. What's SW0? So push buttons to electrical engineers are also called switches. So SW stands for switch, and 0, this is the 0th button. This is the 0th LED, and there's actually a 0 silk screened onto the board there. And over here next to this pair of LED and button is number 1. So this is SW0 and this is SW1. We're going to be using SW0 a lot in the next couple minutes. So that's what SW0 is. Almost every sub part of this demo asks you to press SW0 to go ahead and advance to the next part of the demo. So as is the case, it tells you to go ahead and press SW0. Now it's already started running code for the next part of the demo. If you go back and look at the message, it tells you to switch the LEDs jumper to the RGB position. Right, pull the jumper up, stick the jumper down on the RGB position, and you can see that it is pulsing the red, green, blue LED, which is between the switches, red, then green, then blue. And once you have seen that and are tired of it, you press SW0 to continue on to the next test. So this test demo tells you to press SW0 to start and to optionally open Moo's plotter window. I don't optionally want you to do it, I want you to do it. And then rotate the pot and then press SW0 to continue. So SW0 to start and to finish, and then we want to go ahead and open the plotter window. So we go up into the icon bar and hit plotter, and you'll notice that it's split the serial window horizontally, and now you have a plot window to go with the serial window and your code window. So to actually start this part of the demo, you press SW0 again, and you'll notice that there's some print output showing up in the left-hand screen. It looks like a single-valued tuple. And in the right, you see that it looks like it's trying to plot something. So it's telling you to rotate the potentiometer. And as you rotate the potentiometer, you can see that it changes the plot value. So this is actually really cool. Well, I think it's cool. So it's actually a very nice feature of Moo, is that you can print out a stream of values and have them plotted in real time just by making the output look like a tuple. Moo recognizes that, hey, that's a tuple. I'm going to go ahead and I'm going to plot it, assuming you have the plotter window open. If you don't have the plotter window open, It does, of course, it doesn't make any attempt to plot it. But if your plotter window is open, you can plot as many axes if you want. If this tuple had 4 elements in it, 4 elements separated by 3 commas, it would plot 4 axes out in different colors in the plot window. So it's a really cheap and easy way of doing plotting if plotting is something you've got your heart set on doing. So if you remember, so when we're done with this, so get a sense for how the values change as you move the potentiometer. Notice the range. Notice how smooth or jerky it is depending on how you move the pot, because you'll be asked in the formal part of the lab as one of your questions to kind of discuss how you think all these devices kind of work, and paying attention to what you see in the plot window is going to be helpful for that exercise. So when you're done with that, press SW0 as you were told, and it'll go on to the next test. So the next test is, I'm going to page to where we are in the lab, just so we don't get too far behind. We talked about everything here. Yep. So the next part is, okay, shows you the potentiometer, shows you the prompt, shows you the plot. Okay, so rotary encoder. So it's telling you to twist the encoder knob both directions, then SW0 to continue. So this is the rotary encoder knob right here. And as you crank it one direction, you'll notice that it's chosen to print out higher values. And then as you turn it the other direction, it decreases those values or increases depending which direction you start. So also notice how the values are plotted here, kind of what this motion is. It's jerky, it's not smooth like the other one was, like the potentiometer was. So to finish this test, it said press SW0 to continue. Now, this is one difference, again, between the 1.0 and the 1 kit, 1.1 kit. So both kits have an encoder knob. When you press down on them, you'll notice that they also click. So built into the shaft of this encoder is a button. Just like if it were a volume or a tuning button in like a home or car stereo, typically you press it to turn on and off, and then to tune it or to change the volume and twist it back and forth. So the 1.1 version of the kit, as we just saw, because I pressed it in advance to the next part of the test, in the 1.1 kits, the button that's built into the shaft is electrically connected to the board and the yellow board, and from the yellow board to the rest of the kit. On the 1.0 version, even though it has that button, it's not electrically connected to anything. So sorry, 1.0 kit users, you don't have access to the encoder button. So when you're running the 1.0 version of the test for the demo, I don't believe it even asks you to press the encoder switch to continue. If it does, it'll tell you to skip. If you want to skip that test, press SW0 to skip over it. I don't remember which way the code is written, frankly. That's one difference for 1.0 kit users. So don't worry, 1.0 kit users, you have something else that the 1.1 kit users don't. So don't feel like you're left out. So back to my 1.1 kit. So I already pressed the encoder button, and it automatically advanced since there wasn't any confusion about what it was supposed to do next. It went ahead and went on to the next part of the demo. So the next part of the demo is SW0 to start, wave your hand over the ALS sensor, then press SW0 to continue. ALS stands for ambient light sensor. The light sensor, the ambient light sensor is, I don't have any good pointing device. The ambient light sensor is kind of in the middle of this board. Now, usually I tend to handle the kit like this. I don't know why I keep on turning it sideways, maybe because that's the way the camera is oriented. The ambient light sensor is over here, halfway down on the board. So I do have a decent light source shining on this. So it wants me to start the test by pressing SW0, and we are plotting again. A stream of values is coming out. Now, as I wave my hand over the sensor, as I was told to, you can see that it detects the change of light level that's falling on that sensor. And if I was to do this in really bright light, in fact, if I move it closer to my light source, it actually saturates to its maximum value of 1.0. And as I move it away and then manually darken it, it gets pretty close to 0. So as you were instructed in the safe handling part of the documentation for the kit, try not to touch the board. So I'm shielding it, but not really touching the board. So that's the test of the light sensor. And as you can see, single value tuple, single plot axis, just like the potentiometer and similar to basically how the rotary encoder works. So just like every other test, SW0 to continue. So the next demo test part is press SW0 again to start printing the temperature, then again to continue, of course. So if you press SW0, it takes a couple samples and then it prints out both in plottable form, that single tuple on a line, and then on a line that isn't formatted as a tuple, it actually tells you what the degrees Celsius is. So the number that's in the tuple is the difference from the baseline temperature that it sampled when it first started to run that subtest to now what the temperature difference is. So it's pretty common for it to be offset from 0. I don't quite know why. Maybe just because I just don't take my time and sample it long enough to let it get the correct temperature. But so what is being plotted out is the temperature. And because of the resolution of the temperature, you'll see it jump around a little bit over in the plot window. So the accuracy or the resolution is, looks like it's roughly on the order of maybe 1/8 of a degree Celsius. That's about what that looks like. So the way to actually change the temperature in kind of a meaningful way is if you're in a cool enough room and your breath is hotter than ambient, you can just exhale and you can see the temperature shoot up a little bit. If you're in a warmer room and your breath temperature isn't all that different from ambient, if you breathe out farther from your diaphragm onto the temperature sensor without spitting, please, you can see it shoot up a lot more. You can see I'm pretty hot, if I do say so myself. So I can jack the temperature up 4 degrees just from breathing deeply on that temperature sensor. So it's plotting out temperature in the plot window just by printing out tuples. And the reason you may ask, well, so why did I do this from delta 0? Because if I were to plot the Celsius temperature directly, the mu plotter always has 0. Well, I'm playing with the board. So interesting, the temperature sensor is jumping around like that. I actually can't explain that. Maybe the humidity from my my breath. I'm gonna blow it off now. Let's see if I can get it to. So there might be an artifact from the moisture from my breath, even though I didn't spit on it, I swear, causing the temperature sensor to jump around like 2 degrees. Hopefully it'll settle down. So what I was saying is if I were to plot basically the Celsius values, which are around 25, 0 is always in the center of the plot, and 25 would be up a lot higher. As the temperature changes by a couple of tenths, you would basically just see a horizontal line in the plot because the difference between 25.1 and 25.2 on a 0-based plot is very small. I chose to subtract off kind of the ambient, the center value, and just print the delta. And because the deltas relatively vary over a much wider range, they're more significant on the plot. And that's the reason why I print out both sets of values. Because one is meaningful to us and one is meaningful to the plotter. Okay, hopefully my temperature sensor will stop steaming. Okay, probably okay. So the test said press SW0 to continue. And I don't know if you heard that, but it played a little tune. Probably should have warned you about that first, but I didn't realize it was coming. So what you heard was the speaker on the board. The speaker is this 1/2 inch on a side square, black square that's next to the encoder. That is a tiny little piezoelectric film speaker. It's got great fidelity like you would find in a microwave or a 30-year-old handheld Game Boy kind of thing. You're not going to be jamming to all your favorite tunes on the speaker. That's not really what it's intended for. However, for, I don't know, 10, 15, 20 bucks, you can get a speaker and an amplifier board. It plugs into your Feather. In fact, if you have the header soldered in to this extra spot on the board, you can plug it in and wire up a regular old, however many watt amplifier it is. You can buy quarter, half watt, 1 watt amplifier boards, and you can also buy like a 20 watt board. So you can plug in 20 watt, like car stereo speakers, small car stereo speakers, and you can actually read music data like an MP3 off of the flash file system that's on your Feather, and you can play it, and it sounds just like it came on your stereo. So we're not going to be doing that in ME30. If I have time before the end of the semester, I'll try and demo some cool things like Wi-Fi and Bluetooth and some audio and maybe even voice recording and playback and stuff like that. But with additional accessory boards, with this hardware, you can do a lot of cool things. And I hope to show you more of those in this class. So after it played the little tune, it went ahead automatically to the next part of the demo, where you are instructed to use the encoder to move the servo back and forth, and then the encoder switch, the switch that's built into the encoder shaft, to center the servo and then continue. So notice when I turn the encoder knob, it moves the servo motor back and forth. You will not see it move the laser because you have no laser. In my case, it actually turns the laser on, and you can see it pan back and forth. And the reason why this construction exists is because there's an exercise we do, I don't want to say most semesters, maybe half of the time, where you can make a sentry gun out of your kit. You can get it to pan back and forth, and you can press buttons to shoot. And if you program it correctly, you can make it make a noise like or pew pew when you press the shoot button. And it's pretty cool. I'll probably do a separate demo video, hopefully in the next couple of weeks, that shows you how that works. But sadly, you do not have your laser pointers yet. Supposedly, they're actually coming on Tuesday. Tuesday being, oh no, oh, it's, Tuesday is, it's not April Fool's Day, so the Chinese weren't lying to me when they said my laser pointers would be here on Tuesday, April 1st. So they're supposed to be coming in DHL. So if we ever meet again in person and you want to get a laser pointer hot glued onto your servo, then for $4 I'll bring you a laser and we'll hot glue it in class or lab or whatever. So if we ever see each other again, sniff, sniff, sad, sad. So the test instructions would say that if you press the encoder knob, so I'll turn it all the way to the right, press the encoder knob, and it centers it. So when I go to hot glue on the servo, I know that this is the center position. So when I hot glue it on, I mount it so that it is actually pointed straight ahead at this point. If you just were to pop it off because the hot glue came loose and just hot glue it yourself back on, you should write a program to center it, or you can run the demo so that you know at what point the servo is pointed straight ahead so that you can reglue the laser pointer back on. So after I press the encoder button, it's telling me the test is complete. So you probably noticed that I go back and forth between referring to this program as the test program or the demo program. This demo program evolved from the test program that I run on every board. It's very similar. It does almost exactly the same things, except for as a test program, I don't even want to take the time when I'm testing kits to fire up Moo and open up the serial window and the plotter window. The version of the test program actually gives me feedback using other devices on the board that the component that I'm testing is actually active. So just like the demo program, when you press the button, it turned on the LED. In the case of the servo program, I believe it actually probably dims and brightens the RGB LED that's on the board. So that way I can run it without any feedback, and it's a lot faster for me to get. So this demo program evolved. It does a lot more plotting than, in fact, the test program doesn't do any plotting. The demo program does a lot of plotting because that's what you're more interested in, and it makes for certainly a much more compelling demonstration for you guys to see your kit work for the first time. So that is it for the kit demo. Let me talk briefly about what the 1.0 kit users would see. So when they're asked to do their demo, I am not going to do it because this video is already getting kind of long. I believe the prompt is for you to use these buttons to pan the servo to the left and to the right, and then you use this button to center the servo, and then it advances to the end of the test. So that's the difference in the 1.0 version of the demo versus the 1.1 version of the demo. So you will notice that there's 3 buttons on this board for which there's no equivalent on the 1.1 kit. In reality, 2 of these buttons are electrically exactly the same as these. So if I were to press, I forget which one's mapped to which, but there's only 1 extra button on the 1.0 version of the kit. Not so coincidentally, that 1 button replaces the button functionality that you don't have here. So in reality, both versions of the kit have 3 buttons. Physically there's 5, but electrically there's 3. So 1.0 kit version users, owners have 3 buttons, and 1.0 or 1.1 kit version owners also have 3 buttons. It's just the 2 of them are here and one's here. So let's go back to the lab and let us make sure we didn't leave out anything worth talking about. No, that is pretty much it. And there is a troubleshooting section at the bottom. And it basically talks about, okay, this is a good thing to talk about. So if you think you should be getting serial output in Moo's serial window and you're not seeing it, what often happens is every time you reset the board, either because you plug it or unplug it, or if you actually press the reset button that's on the blackboard, the serial window that's open gets lost and it needs to be closed and reopened again. So let's show you an example of how this might work. If I get rid of the serial window and the plotter window. In fact, it's not always the case that you need to close and reopen the serial window, but frankly, almost every time I rerun my code.py by focusing in the window and hitting save, I tend to just, without even thinking about it, I close the serial window and I open it again. That way I know it's always open at the beginning of the program when I go to run it. So the order is, I'm over here in my code window, I make some changes, and I want to run it again, but I also want to see the messages. So before I hit save, I open up a new serial window, I click in the code window, I hit save, and not only do I not miss my messages, but I get them, because if you had reset the board in some fashion, the serial window basically would have been dead. So let's say I want to run it again because I missed something. So I would close the window and I would immediately reopen it. I'd go back in my code window and I'd save it again, and it would run it again from the beginning. So if you think you're supposed to get serial output and you're not seeing it, just close the serial window, open it again, and then rerun your program from the beginning. If you don't want to run it from the beginning again, I believe that serial output will just go ahead and it'll pick up the print messages that would come later in the program. So you can jump in with the serial window in the middle of a run, and I believe it catches all the subsequent print output. You don't have to have the serial window open from the beginning. I'm pretty sure. I know I've seen this work in the past. So the serial window can get confused, so you just have to reset it. And I think that's really about it as far as the warm-up lab is concerned. So I hope this helps. There were a couple of questions when we did this as a Zoom session, and I think that by doing this with a camera on the kit in lockstep with walking through the text of the lab, it should hopefully eliminate any questions that you have while you're remote and going through this with your kit and don't have me available to talk to live in a lab session. So I hope this helps. And please go ahead and do the warm up just like we've done here. If you don't have your kit now, get it and go ahead and start from the beginning and run through this. And you should find it very, very quick going, much shorter than it took us to run through this together, because you will have seen this once and you'll be able to run through the demo in 5 or 10 minutes. So I hope this helps. Enjoy your kit.